Now we're going to talk about how to determine the continuity of functions if we only have the algebraic equation. So now I won't have the graph to look at. I think this is a little bit more difficult just because it's not as visual, but these properties here are really going to help us out. So let's talk about those. The first one here says that polynomial functions are continuous everywhere. So if you have a polynomial, you can just say, you know what, that's a polynomial, it's continuous everywhere. There's not any work to show, which is really nice. You just get to say, well, it's continuous on negative infinity to positive infinity. So that's a really nice case. 2, rational functions. In rational functions, if you have trouble identifying rational functions, these are the ones that kind of look like fractions. So rational functions are continuous everywhere except the x values that make the denominator 0. And remember, well, what was happening there? Why do we care about those? Well, if the denominator is equal to 0, let's say if the denominator is equal to 0, then we either have a hole in our graph or we have a vertical asymptote. Either way, that's a discontinuity. So if all we're interested in is determining where a function is continuous, then I don't really care which one it is. I just know that both of them are discontinuities, and we want to avoid those. So okay, that's rational functions. That's not too bad. I think the trickiest of the bunch here is going to be these root functions. So here we have the nth root of f of x. So first we have to break this up into two cases. We're going to talk about if n is odd, first of all. So here, if this number, if the index of your root is odd, so we might be talking about like a cubed root or a fifth root or something like that, then the whole function, the nth root of f of x, is continuous everywhere that f of x is continuous. And notice that f of x is really just the inside part of this. We're just looking at the inside part of that. So we're just going to look at that inside part and determine, okay, where's that inside part continuous? And if it's continuous everywhere, then your function is continuous everywhere. If n is even, on the other hand, so if this number right here is even, now we're talking about, say, like a square root or a fourth root. Again, we have the same condition. The nth root of f of x is continuous everywhere that f of x is continuous. So here, again, that's just that inside part that we talked about last time. And non-negative. This part's new, and this and non-negative here is really just to avoid imaginary numbers. So we're avoiding square root of negative numbers here, and that's just because we want to restrict ourselves to real numbers. We have plenty enough to worry about here with just real numbers. We don't want to add imaginary numbers into the calculus mix too. So here we're going to look at a few examples. We're going to be given the equation of a function, and we just want to determine where each function is continuous. So first up, I have r of x equals x squared divided by x plus 1 times x minus 4. You might first of all want to identify what type of function this is. This looks like a fraction, so I know that this is a rational function. So if it's a rational function, if you need to scroll back up, a rational function is continuous it's continuous everywhere except x values that make the denominator equal to 0. So I'm going to look at this one and say, okay, my denominator, it's nice, it's already been factored for me. X plus 1 times x minus 4. We'll take that, set it equal to 0. Well, it's factored for me. I can take each factor and set it equal to 0. So x plus 1 equals 0, and x minus 4 equals 0 gives me x equals negative 1, and x equals positive 4. So I certainly could say, well, my function is continuous everywhere except for x equals negative 1 and x equals 4, because those are the points of discontinuity. But again, I'm really going to encourage you to use interval notation wherever you can, because we're going to be using it so often in our class. So here I'm going to show you how to write interval notation. I think it's a little bit more difficult here in these cases than it was in the last one, because we don't have that visual graph to help guide us. So what I'm going to do is I'm going to draw a number line here. So I'm going to put negative 1 and positive 4 on my number line. And essentially what I'm saying here is I'm saying that this function is continuous everywhere except for these 2 points. So I really have broken my number line up into 3 chunks. I've got this piece right here that's everywhere to the left of -1. So how would I write that? Well, the left-hand side, well, that just goes to -infinity. So -infinity to, looks like that interval stops at, -1. And we want to say that our function is not continuous at -1. And the way we do that is with parentheses. Next, I want to talk about this little area right here between -1 and +4. So it's contained between -1 and +4. So that interval looks like -1 to +4. And then afterwards, this right-hand interval over here, starting at +4 and working our way towards +infinity. So we would say +4 to +infinity. Again, you can use either commas, or more likely, I believe my math lab's really going to want you to use union. So we'll put a big U in between those. And this is our interval of continuity. We would say our function is continuous on these three intervals. So very cool. Part B, f of x equals x to the fourth plus 2x plus 1. This is a really nice case, because this is a polynomial. Polynomials, just to recall, remember polynomials, they have positive whole numbered exponents of your variable x. So here we have all positive, I should say all positive, or non-negative exponents of x, and they're all whole numbers, so it's polynomial. It's continuous everywhere. So sure, you could say continuous everywhere if you really wanted to. But the way we would do that using interval notation is we would say, well, it's continuous on -infinity to +infinity. So just for all real numbers, it's continuous. C and D are going to look very similar here. I've got the square root of x minus 4 and then the cubed root of x minus 4. So here, this one's a little bit trickier because we have this radical to deal with. First of all, you need to remember, if we scroll back up, it really just depended on what's the value of n. What's this guy right here? So, okay, C's maybe a little bit tricky because I don't know what my value of n is right here. There's not one written. Well, think about if we're talking about a square root, we're probably talking about an index of 2. If there's not one written, we're going to assume that that index is 2. So that means that my index is even, which really means I need to be worried about imaginary numbers. So I'm going to do one thing first of all. First, if I go back here, remember we said we need to check that the inside part, f of x, is continuous. So I'm going to check here, hey, is x minus 4, is that continuous everywhere? Well, x minus 4, that's a polynomial, that's continuous everywhere. Continuous everywhere. So that part's really not going to give me a hard time. What I am worried about is where that inside part, x minus 4 might be negative. So I'm going to say, you know what, I want this x minus 4, I want that to be greater than or equal to 0. And now I just have this little inequality that I can solve. This one's not too bad. X is greater than or equal to 4 if I add 4 to both sides. So I basically want to be able to talk about this inequality in interval notation. I could say, well, this function is continuous for all x greater than or equal to 4. But again, I want that practice with interval notation. So let me change my color up here. If we make it just a little number line, here's 4. If x is greater than or equal to 4, we're talking about all of the numbers to the right of 4 here. And if we see that or equal to part, we're saying that x is greater than or equal to 4. So we do want to go ahead and include 4. So if I wanted to talk about where this function is continuous, I would say that this function is continuous on 4 to +infinity. So let's contrast that with part D right here. Part D, I have almost the same function, I just have a cubed root instead of a square root. So if we're working with a cubed root, here our index is odd, so we're just checking that inside part, and we kind of already did that. We looked at x minus 4. X minus 4, that's a polynomial. So that's continuous everywhere. I don't need to worry about negative numbers on the inside of my radical because in this case I have that odd that odd index. So I can just say, you know what, the inside part is continuous everywhere. We have an odd index here, so this is continuous on negative infinity to positive infinity. So odd roots are usually a lot easier to deal with than even roots. One more of these before we talk about a piecewise defined function here. Here I have v of x equals the cubed root of x minus 4 over x plus 2. So again, first thing I want to do is check the index here. The index of my root is odd, so okay, I don't need to worry about where this is positive or negative. What I do need to check out this time is I need to check out that inside part of my function, x minus 4 over x plus 2. Because this function, this v of x, is going to be continuous everywhere that this inside part is continuous. So this time I don't have a polynomial on the inside of my function. This time I have a rational function. So I need to think about, okay, where are rational functions continuous? They're continuous everywhere except for x values that make the denominator equal to 0. So I'm going to take that denominator, x plus 2, and set it equal to 0. So I can solve this equation just by subtracting 2 from each side, so it's continuous everywhere except for negative 2. So if you need to, you can draw out a number line here. This one isn't as difficult as the one we looked at earlier, though, because I want to say, well, it's continuous everywhere except for negative 2. So it's continuous on the left-hand side over here of negative 2. It's continuous on negative infinity to negative 2. And it's continuous on the right-hand side. So starting at negative 2 and working our way towards positive infinity. So negative 2 to positive infinity. So for the most part, the types of functions we work with 99% of the time are going to fall into one of those three categories, right? It's going to be a polynomial, it's going to be a rational, or it's going to be a root functions. And you just, I think the most important part is just figuring out which one of those functions that we have. But that 1% of the time, though, we might be dealing with something like a piecewise defined function here. So here it says locate all points of discontinuity of f of x, and here I have a piecewise defined function. It's x squared if x is less than or equal to 1, and 2x if x is greater than 1. So one way I could go about this is I could graph it. Absolutely. You could go, if you're feeling confident in your graphing skills and your understanding of piecewise defined functions, we could go ahead and do that, but I actually don't think that's the best way to solve this problem. For a piecewise defined function like this, I'm first of all just going to start by looking at how the pieces are defined. So let's look at each of them. X squared, well, that's a polynomial. That's continuous everywhere. So that's continuous on negative infinity to positive infinity. And really what that tells me is how that function is defined is not going to be an issue. So don't need to worry about it. 2x, same deal. Also a polynomial. So it's also continuous on negative infinity to positive infinity. So this is great for me so far because it tells me that I'm really not going to have too many issues. The only potential issue I might have that I haven't talked about is where this function changes gears. It's changing here at 1. So I might want to check, well, what's going on there at 1? And for that, I'm going to fall back on my 3-point checklist for continuity, right? I'm going to check to see, okay, first of all, does the limit as x approaches 2 of f of x, does that exist? I'm going to look at the value of the function, and then I'll compare those two things. We'll make sure that they're equal. So here, limit as x approaches 2 of f of x. For a piecewise defined function like this, it's easiest to break it down into its parts. And actually, I don't know why I said 2 there. My mistake. I should say 1. Limit as x approaches 1 of f of x. There we go. And the 1, just to kind of fix my error, I apologize, is coming from this guy right here. That's why I'm looking at it. So the limit as x approaches 1 here, for a piecewise defined function, it's probably easiest to look at the left and the right-hand limit. So the limit as x approaches 1 from the left-hand side of f of x, and let's clean this up over here. So for the left-hand side of f of x, the left-hand side I'm talking about values which are less than 1. So I'm going to take 1 and plug that into my function x squared. So this is 1 squared, which is, of course, just 1. Now I'll check the right-hand limit. The limit as x approaches 1 from the right-hand side of f of x. This time around, I'm going to take 1 and plug that into 2x, because on the right-hand side, we're talking about values that are greater than 1. So let's see, 2 times 1. This time I get 2. So the left-hand limit is 1. The right-hand limit is 2. The left and the right-hand limits are not the same, which means that the limit as x approaches 1 of f of x does not exist. So what I've determined is that this function is discontinuous at x equals 1. And because I went ahead before and I checked x squared and 2x, because those are polynomials, I know that this is the only point of discontinuity. So you could say, okay, this is discontinuous at x equals 1, and because of the way this is phrased, it says locate all points of discontinuity. I think you could probably leave your answer like this. Alternatively, if you wanted to get the practice with interval notation, we would say that this function is continuous on negative infinity to positive 1 and positive 1 to positive infinity. So either one of those, I would actually just say for these, just go ahead and tell me where that function is discontinuous, since that's exactly what the problem is asking us for. So we're going to use this idea of continuity to help us develop a theorem that will actually help us solve more complicated inequalities in the next video. So that's something to look forward to in the next section.